Assalamualaikum. Okay, now we go into the factors that will affect fluorescence. Okay, we will look on the first very significant factor, i.e. structure of the chemical compound itself. Okay, before that, let us recap what is fluorescent molecules, whereby these fluorescent molecules contain a fluorophore, not chromophore anymore, which is a compound, like a chemical feature inside the compound, just like functional groups that can re-emit light upon excitation. Okay, fluorophore typically contains several combined aromatic groups, or planar, or cyclic molecules with pi bonds. Okay, in UV visible spectroscopy, we say that if it is a cyclic, it's only a cyclic molecule without any double bond inside it, it will not be a chromophore that can enable UV absorption. Okay, the same thing for fluorophore. Okay, because it is a complementary method of UV. Okay, it is still requiring aromatic groups that contain all these pi bonds, but in this case, fluorescent need more, which is the rigid structure, or what we call as like extended conjugation system. Okay, it needs more than what chromophore have. We have two types of fluorescent molecule. Okay, one that can like fluoresce by the enhancement of number of fused ring. Okay, when I said a number of, means that you will expect fluorescent compound to have several fused benzene ring. Okay, that is the one that can fluoresce very intensely. And we also have one fluorescent, simple fluorescent compound that can still fluoresce but having lower quantum yield in fluorescence, i.e. benzene. Okay, benzene itself. Okay, benzene itself have a quantum yield in fluorescence, therefore it can fluoresce. Okay, that's simple one. So the keyword is that aromatic hydrocarbons that unsubstituted, okay, that can enable higher quantum efficiency to be increased with the number of ring. So if you have benzene and then you fuse it with more ring, okay, more ring over here, okay, for example over here lah, okay, senang. So you will have extra fluorescent. Let us see why this happened, and always refer back to your Jablonski energy diagram. Okay, understand the internal conversion, and also understand what is the first electronic singlet state, the second electronic single state, and so on. Okay, and then simple heterocyclic compounds do not fluoresce. Okay, heterocyclic compounds. Okay, we will see after this, even though it contain at least one C double bond C, but because it is not a rigid or a fused ring, it will not fluoresce. Because remember, in fluorescence, there is a delay, okay, in the emission of the radiation. Okay, therefore we have to have a compound that have extended like conjugation system to enable this delay, or else it's not going to happen. And then heavy halogen substitution will suppress fluorescence through intersystem crossing. Okay, remember in Jablonski diagram, okay, we have the first singlet electronic state, and then we have, sorry, the second here, this is the first, and then we have, okay, and then we have a fluorescent and also phosphorescent over there. So we have intersystem crossing that will cross this. This is the way molecule actually relax themselves. So when they relax without giving out radiation, therefore you will have less fluorescence because of the halogen substitution. Substitution of carbonyl group tends to suppress fluorescence as well. Okay, let us see on the different structure, okay, that give fluorescence and non-fluorescent effect. Okay, you see over here for the do not fluoresce compound, all these four compound contain at least one chromophore, right? Here, see the bubble C, see the bubble C. Okay, they will absorb UV or visible radiation, and they will give UV visible spectrometry signal. Okay, but it is not necessarily to be fluorescing, because as I said just now, you have to have an extended conjugation system, i.e. the fused ring, so that it will enable the delay, okay, in emitting the radiation, i.e. The fluorescence lah. Okay, so quinoline in this case will fluoresce as compared to pyridine. So you go into the internet, you can find that the pyridine UV spectrum is around 240 nanometer. It will give you maximum wavelength at around 240 nanometer, while quinoline, the fluorescence, will be at higher wavelength. Okay, and usually it is almost towards the visible range. Okay, remember I showed you the spectrum. This is absorption, and then we have also emission. Okay, this is excitation lambda, this is emission lambda. Okay, so the same thing with indole. Okay, the indole will fluoresce as compared to pyrrole. Okay, because of the existing benzene ring over here. These are some fluorescence molecules. Okay, the most popular fluorescent agent is fluorescein. Fluorescein is used largely as a derivative agent, okay, for any non-fluorescing species. For example, amino acid. Amino acid does not contain chromophore nor fluorophore, but scientists want to see amino acid sometimes under the microscope. Therefore, they use fluorescein to be derivatized with amino acid, and it will be fluorescing a fluorescing complex. That means that after you derivatize the amino acid, which is non-fluorescing and that doesn't contain any chromophore at all, it can help to enhance the fluorescent ability. So when you bring amino acid that has been derivatized with fluorescein into fluorescence spectroscopy instrument, it will give you signal. Okay, the same thing for hydroxyquinoline. Okay, hydroxyquinoline ni pernah dengar kan before this? So this is also one of the agent for gravimetric analysis. Okay, last time it is producing a colored complex. Okay, I hope you still remember. Okay, now let us look on how conjugation help to increase the fluorescence. Okay, so fluorescence of linear aromatics. Okay, starting from benzene ring, and then move towards naphthalene, anthracene, and naphtacene. Okay, you see that the quantum yield of fluorescence increased from 0.11 to 0.60, and also the wavelength of excitation and also wavelength of emission increase as well. Okay, why? Because we have conjugation of the fused ring. So the benzene fused ring, okay, in naphtacene is 4 times more as compared to benzene. Okay, because we have prolonged conjugation that can enable the delay in emission of radiation through fluorescence. Okay, so over here you see we have one excitation excitation lambda and 1 emission lambda, and it will be okay, the emission lambda will always be at longer wavelength as compared to excitation lambda. Okay, so this is in contradiction, or what we call as inversely proportional. Whenever the quantum yield of fluorescence increase, when the conjugation increase, you will have less quantum yield for phosphorescent. Okay, remember what is the meaning of phosphorescent? In Jablonski diagram, it says that when the singlet state of the electron, okay, will be transformed into triplet state of electron. So you have phosphorescent over here. So it's easy to remember. So naphthalene having the highest fluorescence ability, but when you have phosphorescent is none at all. Means that in phosphorescent spectroscopy mode, it will not detect anything. And then we go to structure rigidity. The more rigid the structure, they will give you greater fluorescence. This is in contrast if we have a molecule that have simpler structure, or what we call as floppiness in fluorescence, whereby floppiness will like induce vibrational interaction and also increase internal conversion. We don't want to have a lot of internal conversion. We want to have more fluorescent. Okay, rather than changing into lower energy state, we want to have radiation emission through fluorescent. Okay, the floppiness sometimes can be enhanced when you put chelating agent. Chelating agent tend to form complex structure once again. Means that it will provide the conjugation system. Okay, like this. Chelating agent for metal atom, so that the fluorescence will increase. Let us see on the difference between fluorine, which is rigid, biphenyl less rigid because of the absence of one carbon over here. Kan satu carbon di sini. Okay, because of that, it reduce the fluorescent quantum yield by 5 times. Okay, why lack of rigidity in biphenyl happen? This is because of the internal conversion rate. Okay, increase the probability for radiationless deactivation. We want a radiation emission, i.e. the fluorescent, but when we have internal conversion, it is giving you radiationless. Okay, this is the justification and also how to show you. This is to show you how fluorescent complex will enhance the fluorescent signal or fluorescent yield because of the rigidity of the structure as compared to this one. This one, the OH, the hydroxyl part, still can be deprotonated to be something else. Therefore, the conjugation ends there.